So now we're going to go through a few more problems so you can see how random variables can be applied using the normal model. But let's remember how the normal model is calculated. With the z-scores, the way a z-score is calculated is that you put the observation first, subtract off the mean, and divide by the standard deviation. That way what you're doing is you're shifting the data so the center is 0, or the mean is at 0, and the standard deviation of the z-score is exactly 1, and so we can just then use the normal model. We're going to do this for our random variables, and remember that e of x is just simply the mean or the average of that random variable, so we can put that here where we subtract off, and then we can divide by our random variable's standard deviation. So these two formulas are applying the same concepts. You're just subtracting off the mean and dividing by the standard deviation in order to standardize the variable so you can apply the normal model. So as I demonstrated before, one of the ways that this is useful is by predicting how profitable a company could be. So here in this problem, we're looking at insurance policies, and we want to know how profitable the company is going to be if it writes 10,000 policies. But before we get that, let's just do an easier analysis of 3 policies, trying to figure out the mean and standard deviation if the company were to only write 3 policies. The insurance company estimates that it should make an annual profit of $130 on one homeowner's policy, and that's going to vary from policy owner to policy owner. So the standard deviation is capturing that variation between homeowners. So we can write the new variable as the profit from 3 policies, just as summing up the profit from each of the individual policies. So the expectation of y is just going to be the expectation from each of the individual policies, and when we sum that up, that's going to be $390. So much like our problem with 3 egg cartons, we're interested in summing up 3 random variables to create a new random variable. When we want to look at the standard deviation of that new random variable, we have to do it through the square root of the variance of those individual policies or those individual random variables. We can separate these variances out and sum up those individual variances by assuming that each policy, homeowner policy, is independent. So once we've assumed independence and separated out our variances, the next step is to apply the fact that the variance is equal to the standard deviation squared. So we can substitute in the formula for the standard deviation squared into the variance, and you can see I've done that for every single variance. Next, we plug in our standard deviation that the problem gives us, which is 4,000, and we do that for every single standard deviation. So we have the same formula, 4,000 squared, 3 times. So we can just write that as 3 times 4,000 squared. And then we'll square root that for a final answer of 6,928. Now, what we want to do is we want to use this same formula and same concepts, but apply it to 10,000 policies. When we apply these same formulas to 10,000 policies, what we're doing is we're summing up 10,000 individual random variables. So that's for the expectation of that profit from 10,000 variables, we're going to sum up the expectation of those 10,000 policies. So that's going to be 130 10,000 times, and that's going to give us an expected profit of $1.3 million. The standard deviation from the y variable is a little bit more complicated. Again, we're going to go through the square root of the variance, and you can see that our variable is still defined here from x1 plus x2 all the way to x 10,000. When we separate that out, again, we're doing that assuming those 10,000 policies are independent of one another. So we would want to say that the homeowners don't live next to each other, that they're probably randomly distributed throughout the U.S. And so the impact of one policy homeowners isn't going to impact the effect of another policy homeowners. So that's what we mean by assuming independence. And so that's why we can separate them out. And once we have them separated out, we can use the fact that the standard deviation squared is equal to the variance, and that's what I've done here in the next step. And then we input the fact that the standard deviation equals 4,000. So that's given to us in the problem. You can see that there is 10,000, 4,000 squared. So this is 4,000 squared 10,000 times. And that's what I'm summing up here. So that's equivalent to saying 4,000 squared times 10,000. We'll square root that for a final answer of 400,000. So now that we have these two values, the expected value of y is the expected profit from writing 10,000 policies. Now, we're not always going to get $1.3 million. Sometimes we'll get more, and sometimes we'll get less. And so the standard deviation captures the fact that there may be variation in the profit. And so we want to know, will this company be profitable? And what we want to look at is how unusual having a zero profit or negative profit is. So let's calculate the z-score, because the z-score tells us how unusual something is. So when we calculate our z-score, remember we put our observation first. Here the problem doesn't give us a specific number, but to be unprofitable means you make a negative amount. So 0 means you have no profit. And we want to know how unusual is it to have no profit. Anything greater than 0 is obviously going to be profitable for the company. We subtract off then the average expected profit, which is 1.3 million, and then from that difference we divide by 400,000, which is the standard deviation. So again, we're subtracting the mean and dividing by the standard deviation. That gives us a z-score of negative 3.25. So the z-score is negative 3.25, and what that means is having zero profit or an unprofitable company is 3.2 standard deviations below average. And what that means is it's highly unlikely this company is unprofitable. So most likely this company will be profitable. And the way that we can tell that is because of this z-score. Remember the 68, 95, 99.7 rule. In this example, what that rule says is that companies that write 10,000 policies should fall within 3 standard deviations. So 99.7% of companies should fall within 3 standard deviations. A company that makes zero profit is outside of 3 standard deviations. So a company making zero profit on 10,000 policies is highly unusual. So it's very, very likely that this company is profitable. So maybe insurance policies and profit isn't necessarily something that you're particularly interested in. But let's say you're interested in nutrition and dietitian. Let's do a problem that works through something that might be relevant to that. So here we have an example where we have 2 bowls of cereal, a large bowl and a small bowl. And each morning you pour some cereal into each of them. On average, you pour in 2.7 ounces into the large bowl and 1.7 ounces into the small bowl. And so we want to know what's the likelihood that you're actually pouring more into the large bowl than the small bowl. So that is, how much more cereal do you expect to eat by using the large bowl? So what we're interested in is the difference between the large bowl and the small bowl. And that's just, again, a linear combination. So we can create a new variable that is the difference between the large bowl and the small bowl. So we can simply write that new random variable as XL minus XX, where X is just the amount of cereal in one of the 2 bowls. To find the expected value of the difference, we can just use the fact that we can separate these two expected values out and then plug in their two expected values for the large bowl and the small bowl, and that's going to give us a value of 1. So the expected difference between the two bowls is 1. Moving on to calculating the standard deviation, what we're doing is we're looking at the standard deviation of the difference. So sometimes you're going to pour more into the small bowl, and sometimes you're going to pour more into the large bowl. This standard deviation captures that spread in the differences. So again, we're going to go through the variance operator. The definition of the standard deviation is the square root of the variance, and so that's this first step. And all I've done is rewritten the y in terms of the large bowl and the small bowl here. When we separate them out, remember that negative term goes away. It becomes a positive, and that's because when we square that -1 and remove -1 from the small bowl, it becomes a positive term. So this is not a typo here. This should be a positive sign. And then once we have those variances separated out, we can simply plug in the standard deviation squared for the variance. That's the next step. And now that we have the standard deviations by themselves, we can plug in the standard deviations that the problem gives to us, which is 0.2 for both bowls. And once we calculate this out, that gives us a final answer of 0.2828. So using these two numbers, we're going to assume normality and try to figure out the probability that the small bowl contains more cereal. So a way of writing that is by saying the probability that the large bowl has less than the small bowl. And so we put this in terms of our random variable. We can just rewrite this in terms of XL minus XS by moving this to the left-hand side. So this hasn't changed the equality at all. And then as you notice here, this is just the definition of our variable y, is the difference between the large bowl and the small bowl. And so we have the probability that we're looking for in terms of the random variable that we just calculated in terms of y. Now that we have our y variable and the number that it's supposed to be, we're relating it to, we want to calculate the z-score for that number. So here, the difference is going to be 0, and we plug that into our first part of our z-score, subtract off the mean, so this is the expected difference of the two bowls, and divide then by the standard deviation. That's going to give us a z-score of -3.54. So we have our z-score, and we can relate that then back to the probability that we want to find. So the probability that the difference is less than 0 is the same as saying the probability of the z-score is less than -3.54. So these are equal probabilities, and you can look this up on the z-table. I'm going to leave that up to you, but the answer then is 0.0002. So it's highly unlikely that the small bowl would actually contain more cereal. It's not improbable, it's not a probability of 0, but it's a really, really, really small chance that that would ever occur. So that is how you take random variables and start applying them to the normal model. And that's why I have you doing more problems with the normal model again. In the next section, we're going to move away from probabilities, and we're going to start learning to run tests on statistics and looking at how statistics can be used to compare groups of things. But again, we're still going to use the normal model. So getting practice with this normal model is still going to be really useful for you.